Forces are cancelling each other. Agreed? But are the forces cancelling each other in a same line? No. They are separated. When the forces are separated, when the line of action of the force is not along the same line, what does it produce? It produces moment. And what is a special word for two equal and opposite forces with their line of action separated by a distance? Couple force. And what does a couple force produce? Torque. So your dipole experiences zero net force, but a non-zero torque. So let's find out that torque. Okay. F1, F2, two equal magnitude forces acting. If I find out the torque about point O, let's say, comes out to be Q OB cross E. Why? Because QE is the force. I just took Q out common. That's all. Okay. And QAO cross E, club them QAOB plus AO cross E. Right? What is OB plus AO? It is the distance between them, AB. And what happens when I multiply the magnitude of the charge with the distance between the charges? What do I get? I get dipole moment. And what is the direction of dipole moment? The direction of dipole moment is from minus Q to plus Q. So my torque formula is P cross E. Sum up. When an electric dipole P bar is kept in uniform electric field E bar, two things. Net force, 0. Net torque, P cross E. Magnitude, P E sine theta. Direction, by right hand thumb rule. But there is something more than meets the eye. Can I actually make one more very clever statement about torque? I can. But before that, are we settled on the magnitude P cross E? P is sine theta? Okay. P is sine theta. Direction perpendicular to the plane containing the dipole axis and the electric field. There is nothing wrong about that. But this direction is great, correct, but not useful. It doesn't give me instant math advantage. So what gives me instant math advantage? Shall we? Okay. Next slide will tell you something so special about the torque. Meanwhile, torque equals P sine theta. Of course, we are sorted. And the angle theta is nothing but between the P and E. In fact, a simple tip, recall from chapter of vectors. Whenever somebody says angle between two vectors, by default, it is the smaller value when the vectors are attained tail to tail. Even if somebody doesn't accompany this with a diagram, whenever somebody says angle between two vectors is always measured when the vectors are tail to tail and the smaller value. All right? Watch this. Is your P parallel to E? Is the angle theta 0? Yes, it is. Watch second case. Theta 180. Is the angle 180 and torque is still 0? Yeah. Why? Because sine 0, 0. Sine 180 is 0. Are we convinced that in both the cases, the net torque is 0? The net torque is 0. Is the net force already 0? Yes. Are these two positions of equilibrium, right? Well, theta equal to 0 is stable equilibrium. What does it mean? It means that if this is my field line and this is my torque line, right? If you try to disturb your dipole a little away, what does this torque do? It tries to bring it back. That's why stable equilibrium. In this case, if you try to displace the dipole a little away, it tries and completely rotates. What is torque trying to do? Torque is trying to make P bar parallel to E bar. Now, this is advantage. Wonderful. Direction, agreed. Plane, perpendicular. It's a vector which is perpendicular to the plane containing dipole and field. Great. It's great to hear that. I'm not doubting the correctness of it. Usefulness of it. This is useful. Even though both are in equilibrium, in all cases, torque always try to align the dipole moment vector along the external electric field vector.